Hi, I'm going to use this example of golfing on the moon to illustrate the two-dimensional constant acceleration kinematics equations. So the scenario is that we have this golfer on the moon and they hit the ball with a speed of 27 meters per second at an angle of 35 degrees above horizontal, and the ball lands in a 19-meter deep crater. And from that information alone, we can calculate a whole bunch of things. We can predict how far the ball went horizontally, so this distance here. We can calculate the time to impact, and we can also calculate the velocity of impact, what speed and direction were the ball going when it hit the bottom of the crater. So the assumption here is that the ball, once it leaves the golf club, is going to be traveling with constant acceleration under the influence of the moon's gravity. And so we can use the constant acceleration kinematics equations to perform calculations. And the way I start out any kinematics problem, and in fact almost any physics problem, is to gather information first. I don't go grabbing equations until I know what it is I'm trying to solve for and what information I have. So I just look at the picture here, and I can gather some information. The 19-meter deep crater, and that represents some information in the vertical direction. So one thing with two-dimensional problems that you want to be careful about is keeping track of which is in things happening in the x direction, which information is happening in the y direction. This 19 meters is a vertical distance, and it is the vertical displacement. And it's negative because my final position is below my initial position. So I'm using a conventional coordinate system where to the right is positive x, up is positive y. And the ball ends up below its initial position, so its vertical displacement is negative. Okay, another piece of information I can get is from this magnitude and direction of the initial velocity vector, and I can calculate it using a little bit of trig. So the y component of that vector will be 27 times sine of 35, and I throw that into my calculator and I get 15.5 meters per second. Okay, and likewise I can do that in the x direction, so using cosine instead of sine, so 27 cosine 35, and I get 22.1. Okay, so that's pretty much the easy stuff, just taking numbers and categorizing them as x or y, maybe doing a little bit of trig. The hard part is now we need to think about any sort of implicit information given in the problem. And the way I stated it, this occurs on the moon, and we know the free fall acceleration on the moon. We can look it up in a textbook or a table somewhere, and it turns out that the acceleration is 1.625 meters per second squared down. So about 1/6 the gravity on Earth, and so I'm going to turn that into x and y components as well. It may seem trivial to do that, but that's actually important here. So the y component of that free fall acceleration vector is negative 1.625 meters per second squared. And the x component of that vector is 0. Okay, so with the kinematics equations, where we're talking about one-dimensional or two-dimensional constant acceleration kinematics equations, you're typically looking for 3 known quantities, and then you can calculate the other stuff that you want, because the equations typically have 4 variables in them, depending on how they're written. But what I want you to do is perhaps pause the video. We know the vertical displacement, we know the initial velocity vector y component, and we know the y component of the acceleration, and I want to calculate the time interval. I'm just choosing that somewhat arbitrarily to calculate first, and so I want you to think about which equation you would use along with these 3 known quantities to calculate the time interval. Okay, I would recommend using this one. Okay, that equation has the three knowns plus the unknown time interval. And so that's actually a quadratic. The math is a little bit tedious, so I'm going to skip over that part. But if you plug in these three numbers and then have your calculator do a quadratic solver or use quadratic formula, your calculator will tell you that the time, typically quadratics have two roots, so it gives you minus 1.15 seconds or positive 20.23 seconds. Okay, so which one makes sense to you physically? Did the ball hit the bottom of the crater 1.15 seconds before we hit it, or did it land in the crater 20.23 seconds after we hit it? Okay, well, sometimes the equations give you nonsensical results, and so this one is physically nonsensical. So it's this one that's our solution for the time, or time interval. Okay, so I'm 1/3 of the way there. I've got my time interval. And so this number actually I can bring over to the x side and calculate the horizontal displacement. So I'm just going to go ahead and rewrite that the time interval is 20.23 seconds. And then now I have three things in the x direction, and I can calculate whatever I want over here as well. So the horizontal displacement, delta x, is actually fairly trivial to solve. We would use what I call 6th grade kinematics. Distance is speed times time because the acceleration is 0. So let's do that. So 22.1 times the time of 20.23. And I throw that into my calculator, and it spits out 447 meters. So that's how far. Obviously, this isn't to scale. The person hitting the ball this fast in that direction into a crater 19 meters deep would launch the ball this far. Okay. So last thing to calculate is the final velocity. So I just have to grind out the calculation for that. Why don't you think about a method you might use using all of this information here to calculate the final y component of the final velocity vector. Okay, so go ahead and pause the video, think about that, and then I'll do it. Okay, so there's several choices here. I think this is probably the most straightforward. Okay, so we can throw in those numbers. Y initial 15.5, acceleration negative 1.625, time interval of 20.23. Okay, and I throw that into my calculator, and it spits out a final velocity of negative 17.4. Okay, just running out of space here. V final y, negative 17.4 meters per second. Okay, so that's half of the final velocity vector. I need to find the x final velocity. And this thing I can just assert because there's no acceleration. V initial x and V final x are going to be exactly the same. I mean, you can look at this formula just substituting the y's for x's. There's no acceleration, and so the V final x will just make the assertion is equal to the initial velocity of 22.1 meters per second. Okay, so I'm basically done. I have the time, I have the x and y components of the final velocity, I have the displacement. Another thing you could do is calculate, just using vector arithmetic, convert these x and y components back into back into a speed and direction. So I'm going to skip over that. That's just vector math. But V final, square root of sum of the squares of these would be 28.1. And then the direction of the velocity vector as it hits the ground, using the inverse tangent of the y component over the x component, would be minus 38 degrees. So this is just another way to report the final velocity vector. Okay, so I used the two-dimensional constant acceleration kinematics equations to calculate the time to impact. I calculated the distance, and I calculated the speed and direction of impact. Okay? Thanks for watching.